So welcome to our presentation on new algorithms for computing field of vision over 2D grids from Evan Debenham and Roberto Solis-Oba, University of Western Ontario. In this presentation, I will cover three distinct topics. First, I will give an introduction to what field of vision is and the current state of the art for field of vision algorithms. I will then explain our two proposed new algorithms that aim to improve on the performance of field of vision computation at high field of vision grid sizes. And lastly, I will provide an analysis and conclusion, comparing our algorithms with the current state of the art and showing that they provide improved performance at high grid sizes. Firstly, an introduction to field of vision. A field of vision, or FOV for short, is a representation of all visible locations from a source position in a game environment. And games calculate field of vision using a two-dimensional grid. This image is an example of a simple game which uses field of vision. Here you can see the field of vision grid cells highlighted over the game environment with pink lines. Games generally use field of vision for two major purposes. Firstly, to provide rapidly accessible visibility information, to be able to determine, for example, if one game actor can see another game actor or a particular location. And field of vision is also used to display something called a fog of war to the game's player, which is a visual darkening of areas that aren't visible to the player character. The fog of war can be seen in this scene here with the darkened cells. And this is useful because it communicates to the player what areas their character cannot see. There may, for example, be an enemy lurking in one of those darkened cells that the game is choosing not to show to the player. Notice as well how the darkened cells of the fog of war perfectly line up with the superimposed field of vision grid. When games calculate field of vision, they take in a field of vision source position that is located in the center of one cell, and some cells are defined as vision blocking. The grid shown here is a data representation of the previous scene that an FOV algorithm would use. The vision blocking cells in this case represent walls and are shown here in yellow. The field of vision source represents the position of a specific character within the game, usually the player's character, and in this case it is shown here with the letter S. A field of vision algorithm must then label all cells as either visible or not visible. And a cell is considered to be visible if any part of it is visible from the center of the field of vision source cell. Here's a visual representation of the resulting field of vision for that input grid and field of vision source position, where the non-visible cells have been darkened. Note how this perfectly matches with the scene shown previously. Field of vision and fog of war are often used in games where the player views the game world from above. It's important because the perspective of the player is separate from that of their character, and so highlighting which areas the character can see helps bridge that difference. It's also very common in games where there are a large number of game actors, and therefore the rapidly accessible visibility information is helpful. This is very common in strategy, role-playing, and simulation games. This is a short list of popular games which utilize fog of war and FOV. The most popular existing field of vision algorithm is recursive shadow casting. It's popular due to its relative simplicity and performance. Recursive shadow casting splits the field of vision grid into 8 octants centered on the field of vision source position. Here is a visual example of that. Note how the octants are centered on the field of vision source, not on the center of the grid. Recursive shadow casting then scans by rows or columns, setting each cell within each octant to visible as it goes. Shown here is the order in which the algorithm traverses these octants. So let's step through a simple example of how recursive shadow casting works. Shadow casting starts by using rays to determine the bounds of the space that it will traverse and assign visibility status to cells. A ray is a line cast from a source position towards a destination. In this case, all rays are cast from the center of the field of vision source cell. The algorithm starts with 2 rays that are placed at the edges of the octant, which means that the algorithm is traversing the whole octant. The algorithm then traverses by rows from left to right, bottom to top. In this case, we compute the first 3 rows without encountering any vision blocking cells, but do encounter vision blocking cells in the 4th row. In this case, recursive shadowcasting must split its traversal in two. Two new rays are cast, shown here, creating two separate regions of visible space. The initial traversal continues, shown in blue, and a new sub-traversal continues, shown in pink. These traversals span the range of the space that is within each set of rays. It's important to note that shadowcasting considers a cell to be visible if any part of that cell can be seen from the center of the field of vision source cell. And this is why we traverse through cells that are only just barely touched by those visibility rays, such as the cell to the right on the pink traversal. And this is the resulting field of vision for those traversals. Every cell that we have scanned has been set to visible, which means only a single cell is left as non-visible. Recursive shadowcasting has a time complexity of O of n squared, as its performance depends on the number of visible cells, which scales quadratically with the size of the field of vision grid. Importantly, recursive shadow also does many operations per visible cell. It must calculate grid coordinates, check whether the cell is vision blocking, possibly cast rays, and assign visibility statuses. This means that the number of operations that scale quadratically may be very large, and so shadowcasting will be quite slow at high grid sizes. Our first new algorithm that attempts to improve on this calculates field of vision using rectangles. Many vision blocking cells can be grouped into a single rectangle, which means that they are a more compact representation of vision blocking terrain. Here's a simple example shown where 3 vision blocking cells are represented with 2 rectangles. Of course, in a more complex scene, there may be many cells represented by a single rectangle. Of course, because we are no longer dealing with cells on a grid, we must now store these rectangles in a data structure. For this, we have chosen a quad tree. Quad trees hierarchically divide space into quadrants and allow for rapid searching based on location. Crucially, they are also easy to build and update, which is important because we don't want to assume a game environment never changes. There may be some more efficient data structures, but they are often expensive to update, which may not work in all cases. These figures show how a quad tree storing rectangles R1 and R2 from before is laid out. The space each node occupies is on the right, and the structure of how these nodes connect to each other is shown on the left. The root of the tree represents all space, and then the next level divides the space of the root into 4 quadrants named A through D. The second level does not consider nodes A, B, and C as they contain no rectangles. Node D, because it does contain rectangles, is further subdivided into nodes E through H. Nodes F and G store R1, and node H stores R2. A rectangle can be stored in more than one node. So now that we have our rectangles and are able to store them, we must discuss how they actually are used to determine visibility. 2 of a rectangle's 4 vertices will be relevant when determining visibility, depending on the position of the field of vision source. We refer to these as a rectangle's relevant points. The relevant points are the farthest apart among all vertices of the rectangle which are visible to the field of vision source. In this case, the source can see every point except the bottom right one, and so the 2 furthest visible points are at the top right and bottom left corners of the rectangle. We then cast a ray from each of these points away from the field of vision source. The area that is between the rays and the rectangle contains our non-visible space. Importantly, to get the same resulting field of vision as shadowcasting, we consider a cell to be not visible if it is entirely within this space. So there are some cells here which are largely in this space, but not completely, and we consider them to be visible. Also importantly, because we are now determining visibility for an entire region at a time, we can assign visibility statuses to cells in any order we choose. By assigning the cells to not visible by rows from left to right, we assign them in the same order they are laid out in memory. This is taking advantage of a property of computer memory called spatial locality, which improves performance in this case versus assigning statuses randomly. Also, as a performance optimization, we can use the quad tree to sort rectangles based on their distance from the field of vision source, and then skip far rectangles that are occluded behind near ones. So in summary, we are now using vision blocking rectangles, which are a more compact representation of vision blocking terrain and can be stored and efficiently accessed using quad trees. We are also now computing cell visibility using these rectangles, determining visibility for an entire region instead of on a per cell basis. And we can write cell visibility statuses quickly due to spatial locality. Our algorithm is still O of n squared because we must still ultimately assign a visibility status to each non-visible cell. But the number of operations we perform on a per cell basis is now much lower than recursive shadow casting. And so even though the algorithm scales quadratically, the relative performance to shadow casting should be much better at high grid sizes. Secondly, we now present a more complex algorithm that updates an existing FOV rather than calculating from scratch. Field of vision is often calculated as a game actor moves through an environment. And so the previously calculated FOV will be accurate to an adjacent cell to the current one. We can take advantage of this property to reuse the information from the previous field of vision. This is helpful not only because it means we will be assigning a minimal number of cell visibility statuses, just the ones that change, but it also means that we do not need to reset the field of vision grid to default values when we are calculating a field of vision. And at high grid sizes, the cost of resetting is significant. There are additional conceptual complexities, however. We must now consider two field of vision sources instead of one. And rather than just assigning cells, we must only assign the ones that change. In this example image here, you can see two field of visions for positions S1 and S2, and the rays that would have been cast by rectangle field of vision. In order to determine what space is changing visibility, we use cones of changing visibility. A rectangle will have an occluded area for each field of vision source position, and the non-overlapping occluded areas form two cones. In this figure, we can see the rays cast for each field of vision source. The area that is visible to neither source is behind the cones C1, C2, and the rectangle, and the area within each cone is visible to exactly one FOV source. If we invert the visibility of cells within these cones, we will update the field of vision. Importantly, because we want to produce the same result as recursive shadow casting in rectangle FOV, a cell is considered to be within a cone and should have its visibility status inverted if it intersects with the cone but does not intersect the cone's outermost ray, the ray that is furthest from the rectangle. Those rays are labeled here as R1 and R2. It is also important to classify cones based on the visibility of their origin point. A cone's origin point is the point within the cone that is closest to both FOV sources. This will be a relevant point of the rectangle from which the cone was cast. In the figure here, that is the top right point of R1. Visible cones have an origin point that can be seen by both FOV sources, and they are in fact the only type of cone which need to be processed in order to update the FOV. Partially visible cones have an origin point which is visible to only one FOV source. They don't need to be processed because they are always inside of another cone. We know this because partially visible cones are, by definition, in an area of changing visibility, and cones define areas of changing visibility, so they must be inside of another cone. Therefore, we can process the partially visible cone when we process the fully visible cone that it is inside of. Additionally, as a performance optimization, we can use the quad tree to order the cones such that a fully visible cone always precedes the partially visible cones that are inside of it. This allows us to skip many visibility checks when we are determining cone types. And lastly, there are non-visible cones, which have an origin point that cannot be seen from either FOV source. These cones only contain space that cannot be seen by either FOV source, and so they should not be processed. Additionally, we have to consider cases of cones intersecting with further rectangles when we invert them. In this figure here, you can see that a fully visible cone has been shrunk based on its intersection with various rectangles. Cones are always shrunk such that the area occluded behind a rectangle for both FOV sources is removed. The cone's initial rays are shown with dotted lines, but they have been shrunk as they intersect R4 and R3. 3 additional rays are also cast, 2 using R2 and 1 using R4. The region of the cone ends as it intersects with R3 and R5. The total area of this shrunk cone is highlighted. Note, based on the dotted lines, that this is much smaller than the area of the cone before it was shrunk. We must then invert all cells which intersect the shrunk cone, but not its outer ray R1. Here you can see highlighted which cells will be inverted. These are all cells that touch any ray or the inside of the cone, but do not touch R1. Even cells whose corners are just barely touched by R1 should not be inverted here, such as the cell adjacent to R2. So in summary, we are now dealing with cones of changing visibility. There are many more conceptual complexities. We now have two field of vision sources. We must consider cone types and cone intersections. However, we are now using a previous FOV instead of computing from scratch, which minimizes the number of cell visibility status assignments, both because we are reusing the previous grid and therefore only need to change the cells that have changed, and also because we no longer need to reset the grid to default values. I will now show an experimental evaluation on 3 separate environments. For each of these environments, we picked a large number of random field of vision source paths through the environment and are reporting the mean running times for all of the different tests. This should give a good idea of the average performance values for each algorithm in each environment. The first environment uses 160 rectangles to simulate a large indoors environment with various rooms and hallways. Importantly, this environment is very enclosed. There are no long sight lines, so the number of visible cells should be low. We should expect this to be a very good scenario for recursive shadow casting. For each of these environments, we tested with grid sizes ranging from 128 by 128 cells to 4096 by 4096 cells. Because the running times will be much higher for the high grid size, we are not reporting the raw numbers in the bar graph here, but are instead showing proportionals. The slowest algorithm will be 100%, and the 2 faster algorithms are each the percentage of the running time of the slowest algorithm. The raw performance numbers are still shown below. We can clearly see that this environment strongly favors shadow casting over rectangle field of vision due to the lower number of visible cells. However, field of vision update's running time is hardly affected by grid size, only doubling between the smallest and the largest. And so it performs very, very well at high grid sizes here. Our second environment uses 200 rectangles randomly clustered towards the center. This is meant to simulate a more structured outdoors environment, such as a town. The number of visible cells is very low in the center, but very high on the outer edges. In this environment, shadow casting performs much worse at large grid sizes due to the high number of visible cells. And conversely, because of the high number of visible cells, rectangle field division does quite well. Additionally, its lower per cell running time complexity is highlighted here, as it is able to outstrip shadow casting very quickly once grid size becomes large. Importantly, though, at low grid sizes, because the complexity for each rectangle is unaffected by grid size, shadow casting is still able to outperform it. Field of vision update has the longest running time at low grid sizes, again due to that per rectangle complexity, but that running time increases at the slowest rate as the grid size increases, and so it ends up being the fastest algorithm by a fair margin as grid size becomes large. Lastly, the third environment is meant to simulate the game map from the game League of Legends, which is probably the most popular game that uses field of vision today. This environment is a bit of a mix of the previous two. There are some long pathways with large sight lines, and also clustered areas with low sight lines. This environment ends up being a bit of a mix between environments 2 and 3. We once again see shadow casting having the slowest running time as grid size becomes large, and field of vision update having the fastest running time as grid size becomes large. In an environment that is more enclosed, we may see shadow casting perform better, but in this mixed environment, we can clearly see that shadow casting's good running time in closed environments does not outweigh its poor running time in more open ones. So in summary, shadow casting is very slow if there are many visible cells, but performs well when there are few visible cells. Both shadowcasting and rectangle field division are slowed down at high grid sizes because they have to reset the grid. Field division update avoids this and is always the fastest at high grid sizes. Rectangle field division and field division update are slow at low grid sizes when the environment is made of many rectangles. And as grid resolution becomes high, field division update has the best performance. So in conclusion, there is no single fastest algorithm. Shadowcasting performs best in environments with a low number of visible cells. Rectangle field division performs best in environments with medium to high number of visible cells, which also have medium or large grid sizes. And field division update is better than other algorithms at medium to large grid sizes, but an FOV must be calculated using one of the previous algorithms at least once. So for fastest field division computation, we recommend using a hybrid approach. If an algorithm has low visibility or a smaller grid size, calculate with recursive shadowcasting. However, if an environment is more open and has a medium to large grid size, calculate FOV with rectangle FOV first, and then update that FOV as the field division source moves. It's important to note that these recommendations are based on our own tests, and specific game developers may know the environments of their own game better and may want to run their own tests to see what's better for their specific circumstances. However, it is also important to consider the highest running time of the algorithms. In our experiments, shadowcasting's running time maxed out at 46 milliseconds, rectangle field division was 10 milliseconds, and field division update was 1.3. In the world of scientific computing, these may seem like trivially small running times, but it's important to remember that games are real-time applications and will generally attempt to display a new frame of animation to the player at least once every 16 milliseconds in order to give the impression of smooth motion. Games will not have to calculate field division every time a new display frame is drawn, but they must calculate field division fast enough to not significantly disrupt display frame rendering or starve the game of other game processes of system resources. Because of this, taking 46 milliseconds to calculate field division is almost certainly unacceptable, but 10 and 1.3 milliseconds are much more reasonable. Our algorithms are always fast enough to fit within the time to render a display frame. Thank you very much for listening to this presentation. I'm happy to answer any questions.